Okay, good day, students of CS 6201, which is Computer Organization and Architecture. So again, welcome to our virtual class for this afternoon. Okay, so right now, our topic is about interrupt or computer interrupt. So this is week 4. So when we say an interrupt, it is a request from input-output device for service by a processor. So the processor provides requested service by executing interrupt service routine, which is the ISR. The contents of the personal computer general registers and some control information are stored in memory. So when the interrupt service routine completed, the processor is restored so that interrupted program may continue. So when we say interrupt or computer interrupt, it is a signal or it is a computer signal that is sent to the processor to request immediate attention. So when the processor receives this request, it suspends what it is doing and runs the process associated with the interrupt. An interrupt, it is a computer signal which has highest priority from hardware or software, which processor should process its signal immediately. So in early years of computing, the processor has to wait for the signal for processing. So the processor has to check each and every hardware and software program in the system if it has any signal to process. So this method of checking the signal is the system for processing is called polling method. So in this method, the problem is that the processor has to waste number of clock cycles just for checking the signal in the system. So by this, processor will become busy unnecessarily. So if any signal came for the processor will take some time to process the signal due to the polling process in action. So the system performance also will be degraded and response time of the system will also decrease. So to overcome this problem, engineers introduce a new mechanism. So in this mechanism, processor will not check for any signal from hardware or software, but instead the hardware and software will only send a signal to the processor for processing. So the signal from hardware or software should have highest priority because processor should leave the current process and process the signal of hardware or software. So this mechanism of processing the signal is called interrupt of the system. So an interrupt, it is a computer signal. It means it is a signal that tells the computer to stop running the current program so that a new one can be started or a circuit that carries such a signal. So an example of an interrupt is that a signal to stop the Microsoft Word so that a PowerPoint presentation can gear up. So we have two types of interrupts. So although interrupts have highest priority than other signals, so there are many types of interrupts, but basic types of interrupts are, we have the hardware interrupts and the software interrupts. A hardware interrupts if the signal for the processor is from external device or hardware is called hardware interrupts. So for example, from keyboard, we will press the key to do some action. This pressing of key in keyboard will generate a signal which is given to the processor to do action. So such interrupts are called hardware interrupts. So a hardware interrupt, it is, of course, it is an electronic alerting signal sent to the processor. So from an external device. So like a disk controller or an external peripheral devices. So yun nga yung ating example. Like for example, when we press a key on the keyboard or move the mouse, so they trigger hardware interrupts. So which cause the processor to read the keystroke or mouse position. So the hardware interrupts can be classified into two types. So we have the maskable interrupt and the non-maskable interrupt. So when we say a maskable interrupt, the hardware interrupts which can be delayed when a much highest priority interrupt has occurred to the processor. So ang maskable interrupt, it is a hardware interrupt. So that can be disabled or ignored by the instructions of the central processing unit. Whereas a non-maskable interrupt, so the hardware which cannot be delayed and should process by the processor immediately. So a non-maskable interrupt, it is a hardware interrupt. So that standard interrupt, so masking techniques in the system cannot ignore. So a non-maskable interrupt, it is a hardware interrupt cannot be disabled or ignored by the instructions of the central processing unit. So we have some common examples of non-maskable interrupt. So include types of the internal system chipset errors. We have the memory corruption problems. We have the parity errors and high-level errors. So needing immediate attention. So in a sense, a non-maskable interrupt, it is a way to prioritize certain signals within the operating system. So another type of interrupt, we have the software interrupts. So software interrupt can also be divided into two types. So they are the normal interrupts and exception. So a software interrupt, so also called an exception. So an interrupt that is caused by a software. So usually a program in user mode. So examples of events that cause them are requests by an application program for certain services from the operating system or the termination of some programs. So the software interrupt may also be unexpectedly triggered by a program execution errors. So these interrupts typically are called traps or exceptions. So for example, divide by zero exception will be thrown. So a software interrupt is requested. So if the processor executes a divide instructions with divisor equal to 0. So we have two types. So we have the normal interrupts. So when we say a normal interrupts, the interrupts which are caused by the software interactions or instructions rather are called software instructions. So a normal interrupts, the interrupts which are caused by the software instructions are called software instructions. Whereas the exception, unplanned interrupts while executing a program is called exception. So for example, while executing a program, we got a value which should be divided by 0 is called a exception. So exception, it is unplanned interrupts while executing a program is called exception. And then we have the classification of interrupts according to periodicity of occurrence. So first, we have the periodic interrupt. So if the interrupts occurred at fixed interval in timeline, then that interrupts are called periodic interrupts. So the periodic interrupt, so it is the interrupts like a program, okay, is it a parts of which are reacting to the events, so taking place in the microcontrollers. So they are usually used for quick response. So for example, of periodic interrupt, like for example, we will configure the computer to request an interrupt on a periodic basis. So this means an interrupt handler will be executed at fixed time intervals. So this periodic interrupt will be essential for the implementation of real-time data acquisition and real-time control systems. So it is one of the timer, okay, peripherals. It can be used as a trigger for modules like the timer or an analog to digital converter. Okay, so the periodic interrupt can also be used to trigger very simple events, okay, like toggling the states of a pin. Whereas the periodic interrupt, if the occurrence of interrupt cannot be predicted, so then that interrupt is called a periodic interrupt. So those are the two classification of the interrupts. We have the periodic and the aperiodic interrupts. And then we have also classification of interrupts according to the temporal relationship with system clock. So first, we have the synchronous interrupt. So the source of interrupt is in phase to the system clock is called synchronous interrupt. So in other words, interrupts which are dependent on the system clock. So example, timer service that uses the system clock. So that is a synchronous operation, okay, or synchronous interrupt. Okay, so the synchronous interrupts are produced by the central processing unit, control unit. So while executing instructions, and are called the synchronous because it has a control unit issues. So asynchronous operation blocks a process till the operation completes. So an asynchronous interrupts, if the interrupts are independent or not in phase to the system clock, is called asynchronous interrupt. So ang asynchronous operation, it is a non-blocking and only initiates the operation. So those are the two classification of interrupts according to the temporal relationship with system clock. So we have the synchronous and the asynchronous interrupts. And then we have also the interrupt handling. So we know that instruction cycle consists of fetch, decode, execute, and read-write functions. So after every instruction cycle, the processor will check for interrupts to be processed. If there is no interrupt is present in the system, it will go for the next instruction cycle. So which is given by the instruction register. So if there is an interrupt present, then it will trigger the interrupt handler. So the handler will stop the present instruction, which is processing, and save its configuration in a register and load the program counter of the interrupt from a location, which is given by the interrupt vector table. So after processing the interrupt by the processor interrupt handler, will load the instruction and its configuration from the save register. Process will start its processing where it's left. So this saving the old instruction, processing configuration, and loading the new interrupt configuration is also called as context switching. So when we say interrupt handling, it is a key function in real-time software. So, and it also comprises interrupts and their handlers. So the software assign each interrupt to a handler is the interrupt table. So an interrupt handler is just a routine containing a sequence of operations. So each of these may request input and output while running. So the interrupt handler is also called as interrupt service routine or the ISR. So the interrupt service routine, it is a software routine that hardware invokes in response to an interrupt. So the ISR examines an interrupt and determines how to handle it, executes the handling, and then returns a logical interrupt value. So if no further handling is required, the interrupt service routine notifies the kernel with a return value. So there are different types of interrupt handler which will handle the different interrupts. So for example, for the clock in a system will have its interrupt handler. So a keyboard will have its interrupt handler. For every device, it will have its interrupt handler. So the main features of the ISR are first, interrupts can occur at any time. They are asynchronous. So the ISR can call for asynchronous interrupts. So interrupt service mechanism can call the ISRs from multiple sources. So the ISR can handle both maskable and non-maskable interrupts. An instruction in a program can disable or enable an interrupt handler call. So the ISR or on beginning of execution, it will be disable others devices interrupt services. So after completion of the ISR execution, it will reinitialize the interrupt services. So the nested interrupts are allowed in ISR for diversion to other ISR. So those are some of the main features of the interrupt service routine. So we have two types of interrupt handlers. So first, we have the first level interrupt handler is hard interrupt handler or fast interrupt handler. So these interrupt handlers have more jitter while process execution, and they are mainly maskable interrupts. So the first level interrupt handler, it is a software or a hardware routine that is activated by interrupt signals sent by the peripheral devices and decides based on the relative importance of the interrupts. So we have two types, the first level interrupt handler and we have the second level interrupt handler. So it means is soft interrupt handler and slow interrupt handler. So these interrupt handlers are having less jitter. And then we have also the interrupt latency. So what is interrupt latency? So when an interrupt occurs, the service of the interrupt by executing the ISR may not start immediately by context switching. So the time interval between the occurrence of the interrupt and start of execution of the ISR is called interrupt latency. So when we say interrupt latency, ito yung time from the assertion of a hardware interrupt. So until the first instructions of the device driver's interrupt handler is executed. So the operating system leaves interrupts fully enabled almost all the time, so that the interrupt latency is typically insignificant. So we have time taken for context switch, and the sum of time interval for executing the ISR, and the interrupt latency is equals to T switch plus the time of time interval for executing the ISR. So how to fix system interrupts? So the system interrupts is an official part of the Windows operating system and appears as a process in the task manager. So it handles the communication between the hardware and the system. So while this is a good thing, the problem happens when system interrupts consumes a high central processing unit usage. It might be an indication that there is an underlying issue with one or your hardware components or its associated drivers. So it is very important to check the CPU usage or system interrupts now and then. So if it is a high, the first thing you have to do is to diagnose which piece of your hardware or its drivers failing. Then you have to take the appropriate action to fix the issue. So the following article helps you understand how to check the CPU usage of system interrupts and the different methods to diagnose and troubleshoot the hardware issues. Okay, so let us move on to a bus structure. So a simple figure on the connections of the central processing unit and a memory. So the CPU and memory are normally connected by three groups of connections. So each called a bus, a data bus, an address bus, and a control bus. So when we say a bus structure, it is a group of lines. Okay, so as shown in the given figure, it is a group of lines that serves as a connecting path for several devices. Is called a bus. So in addition to the lines that carry the data, the bus must have lines for address and control purposes. So there are types of bus are used. So first we have the address bus. So it carries memory addresses from the processor to other components, so such as the primary storage and input-output devices. And then we have the control bus. It also carries control signals from the processor to the other components. So the control bus also carries the clock pulses. So the bus structure, it is a group of wires which carries information from CPU to peripherals or vice versa. So the bus structure, it consists of a single bus structure. So it has a common bus or a common bus used to communicate between peripherals and microprocessor. So a single bus structure, ito yung one common bus used to communicate between the peripherals and the microprocessor. So it has also disadvantages due to use of one common bus. Whereas the multi-bus, so to improve the performance, multi-bus or the multiple bus structure can be used. So a multiple bus, multiprocessor system, it is a tightly coupled architecture that utilize several yung mga parallel buses to interconnect multiple processors. Okay, shared memory and shared input and output devices. So the multiple buses permit the several devices to work simultaneously. So reducing time spent waiting and improving the computer speed. So in two bus structure, one bus can be used to fetch instructions, other can be used to fetch data required for the execution. So that's improving the performance, but cost increases. So the performance improvements are the main reason for having multiple buses in a computer design. So ang system bus, it is a single computer bus that connects the major components of a computer system. So it combines the functions of a data bus to carry information and an address bus to determine where it should be sent and a control bus to determine its operation. So the data bus, it is a computer subsystem that allows for the transferring of data from one component to another or on a motherboard or in a system board or between two computers. So this can include transferring data to and from the memory, so or from the central processing unit or to other components. So the data bus, it is a data-centric software framework for distributing and managing real-time data in intelligent distributed system. So it allows the applications and devices to work together as one integrated system. Whereas the address bus, it is a computer bus architecture used to transfer the data between devices that are identified by the hardware address of the physical memory, so the physical address, so which is stored in the form of a binary numbers to enable the data bus to access the memory storage location. So we have sample of selected location or the memory location, like 0 location, first location, second location, up to end location. And then we have the control bus. In computer architecture, a control bus is a part of the system bus and is used by CPUs for communicating with other devices within the computer. So the control bus, it is a computer bus that is used by the central processing unit to communicate with devices, okay, that are contained within the computer. So the control bus is a bidirectional and assist the CPU in synchronizing control signals to internal devices and external components. So like for example, we have 2 raised to 3 is equals to 8. Okay, so 3 address line is required to select 8 location. So in general, 2 raised to x equals to n, where x number of address lines or the address bit, and n is number of location. So the address bus, it is an or unidirectional group of wires which carries address information bits from processor to peripherals like 16, 20, 24 or more parallel signals lines. So the data bus, it is a bidirectional group of wires which carries data information bit from processor to peripherals and vice versa. Whereas the control bus, it is a Bidirectional, it's a group of wires which carries control signals from processor to peripherals and vice versa. So yung figure nga shows the address, data, and control bus and their connection with the peripheral and the microprocessor. So it is a simple figure of the single bus structure. So showing the details of the connection. So it is a bus, it is a single computer bus that connects the major components of a computer system. So combining the functions of a data bus to carry information, an address bus to determine where it should be sent, and a control bus to determine its operation. So in a single bus architecture, all components, including the central processing unit, the memory, and peripherals share a common bus. So when many devices need the bus at the same time, so this creates a state of conflict called bus contention. So some wait for the bus while another has control of it. So the performance. So time taken by the system to execute a program. So parameters which influence the performance are clock speed, the type and number of instructions available, the average time required to execute an instruction, the memory access time, power dissipation in the system, the number of input-output devices and types of I/O devices connected, and the data transfer capacity of the bus. And the memory locations and the addresses. So we all know that the memory, it is the second major subsystem in a computer. So it consists of a collection of storage locations, so each with a unique identifier called an address. So the main memory of the computer is organized in such a way that the group of these n bits can be stored and retrieved easily by the computer in a single operation. So the memory locations are addressed from 0 to 2 raised to k. Okay, so the memory has 2 raised to k addressable locations. So, and thus the address space of the computer has 2 raised to k addresses. So in computing, a memory address is a reference to a specific memory location used at various levels by a software and hardware. So the data is transferred to and from memory in groups of bits called words. So a word can be groups of 8 bits, 16 bits, 32 bits, or 64 bits and growing. So if the word is 8 bits, it is referred to as a byte. The term byte is so common in computer science that sometimes a 16-bit word is referred to as a 2-byte word. So, or a 32-bit word is referred to as a 4-byte word. So figure shows an example of a main memory. So it is a digital computer's main memory. So consists of many memory locations. So each memory location has a physical address, so which is a code. So a memory address consists of a zeros and ones. So it is a unique identifier used by a device or a CPU for data tracking. So this binary address is defined by an ordered and finite sequence allowing the central processing unit to track the location of each memory byte. And then we have also the address space. So to access a word in memory requires an identifier. So although programmers use a name to identify a word or a collection of words, at the hardware level, each word is identified by an address. So the total number of uniquely identifiable locations in memory is called the address space. So the address space, it is the amount of memory allocated for all possible addresses for a computational entity. So such as a device, a file, a server, or a network computer. So the address space may refer to a range of either physical or virtual addresses, so accessible to a processor or reserved for a process. So for example, a memory with 64 kilobytes, 16 address line required, and a word size of 1 byte has an address space that ranges from 0 to 65,535. So the memory units, so we have kilobyte, megabyte, gigabyte, and terabyte. So in kilobyte, the exact numbers of bytes, you have 1024 bytes. Okay. Then you have in megabyte, you have 2 raised to 20, which is 1 million or million bytes. You have billion in gigabytes and then trillion bytes in terabytes. So that is the memory addresses defined using the unsigned binary integers. So it is the set of the logical addresses that a process reference in its code. So another example, a computer has a 32 megabytes of memory. So how many bits are needed to address any single byte in memory? So the solution is that the memory address space is 32 MB or 2 raised to 25 or 2 raised to 5 multiplied by 2 raised to 20. So this means that we need log to 2 raised to 25 or 25 bits to address each byte. So another example, a computer has 128 MB of memory. So each word in this computer is 8 bytes. So how many bits are needed to address any single word in memory? So the solution, the memory address space is 128 MB. So which means 2 raised to 27. So however, each word is 8, 2 raised to 3 bytes. Okay, 1, 2, 4, 8. So which means that we have 224 words. So this means that we need log 2 raised to 24 or 24 bits to address each word. Okay, so thank you for listening. So have a nice day to all of you. So stay safe. I'm Dean Jane.